trigger on that fluoroscopic unit?
No, you need a supervisor.
Operator's permit.
Operator license.
It allows you to participate in a fluoroscopic exam, but you cannot step on that pedal. You cannot hit the trigger. Okay? Even with your fluoroscopic certification, that just allows you to perform fluoroscopic procedures with a doctor who has a supervisor or operator's license. There I go again, making things up. Sorry. No, that's true. That's true. You guys can't
The
do that.
exposure?
You can't. Yeah, you can't do that. You can't step on the fluoro pedal.
But the exposure button.
The exposure button, the tech can do with the doctor.
Exposure. Yeah, exposure is different, but you cannot do a fluoroscopic exposure.
You can't fluoro.
Yeah, you can't fluoro.
Oh, you're talking about in the room floor.
Right, exactly, in the room.
Mhm.
Yep. Okay, bucket slot cover. Okay, a cover of 0.25 millimeters of lead equivalent covers the slot when the bucky is relocated to the foot end of the table. So again, here's the bucky, your film tray. When you put the bucky all the way down, there's going to be a slot cover of 0.25 millimeters of lead equivalency to protect you from scatter radiation coming from the table. Okay. You should also have a protective curtain. The curtain or panel of 0.25 millimeters of lead equivalency should also be situated between the patient and the operator. Okay? So there's not going to be a lot of x-rays coming from 90 degrees off the patient. All right? Now, where is the best place to stand during a fluoroscopic procedure? Behind the doctor, or at 90 degrees from the patient. You don't want to be at the foot or the head end. You guys remember that? Okay. Cumulative timer. When you're using fluoroscopy, a cumulative timer that produces an audible signal when fluoro time reaches 5 minutes must be provided. It must be provided. Okay, DAP, or dose area product. DAP, or dose area product. DAP is a quantity used in assessing the radiation risk from diagnostic X-ray examinations in interventional procedures. More specifically, it is defined as the absorbed dose multiplied by the area irradiated. Okay? Because this is what can happen. You can be irradiating an area of, let's just say, 5 milliroentgens per minute. Let's just say that, okay? Like you're only doing a fluoro shot of a small area. But what if you're using the same exact dose of 5 milliroentgens for a larger area? Doesn't that also change the amount of exposure that the patient is receiving? The dose is the same, but you're X-raying or doing a fluoroscopic study of a larger area. This is where DAP comes in. It's more accurate than just identifying dose by itself. It also takes into account the area or the size of the area being irradiated. It's the same slide that you guys have. I think I just switch some of the paragraphs around. You guys are looking at me like, oh, I also flipped the image. You see that? I flipped him. Yeah, I'm trying to make it more unique, so I flipped him the other way. Okay. All right. Now, the intensity of the X-ray beam at tabletop of a fluoroscope should not exceed 2.1 Roentgens per minute for each MA at 80 kVp. Now, fluoroscopic units have an optional high-level control. Okay? If it doesn't have one, this optional high-level control usually works, is incorporated or is utilized when you're dealing with thicker, more dense body parts. It's a boost mode is what they call it. Okay? So it jacks up the technical factors when you're dealing with thick or more dense objects. Now if it doesn't have that, okay, no boost mode or no optional high level control, exposure must not exceed 10 Rs per minute during fluoroscopy. And if it does have it, it does allow you to double the exposure and not exceed 20 Rs per minute during fluoroscopy. Okay, so again, what I do want you guys to know is DAP is the quantity that reflects not only the dose, but also the volume of tissue being irradiated. It's not just the dose. Okay? Up here, DAP increases with larger field sizes even if the dose remains unchanged. Highlight that. DAP increases with larger field sizes even if the dose remains unchanged. And also vice versa, if you have smaller field sizes, it'll decrease. Okay. Everybody got it? Almost? Tell you what I'm going to do. I'm going to send you my new set of slides. It's a good idea? All right. All right. I'll say I never do anything for you. All right. Design for protective barriers. All right. So we talked about the two different types of radiation. We have primary and we have secondary. Barriers are based on the type of radiation that is being emitted in a procedural room. Primary is going to be the most intense, most hazardous, and most difficult to shield. Any wall in which the primary beam can be directed needs to have a primary barrier. These walls are designed with lead bonded to sheetrock or wood paneling. Now, secondary radiation, there are two different types. You have scatter. The primary source is usually the patient. It can also come from the equipment, but it mostly comes from the patient. And the intensity of the scatter radiation at 1 meter from the patient is approximately 1/10 the intensity of the original primary beam. So it's going to be 1/10 the intensity. Leakage radiation emitted in all directions from the protective housing other than the useful beam cannot exceed 100 milliroentgens per hour at a distance of 1 meter. That's the definition of leakage radiation. Leaded walls are not required, but instead gypsum board, glass, or lead acrylic are acceptable materials. It's cheaper. Okay? Factors that affect the barrier thickness. Number one is the distance from the source of radiation to the barrier. The distance from the source of the radiation to the barrier. The area that is being protected by the walls. For example, on the other side here, is it going to be a waiting room? Is it a hallway? Is it a restroom? Okay, is it a pediatric unit? You understand what I'm saying? So that also depends on the type of wall that you're going to use. The area occupied mainly by personnel and patients, this is the controlled area. The design is based around the occupational limits of 100 millirems per week. 100 millirems per week. As a side note, the annual recommended occupational dose is 50 millisieverts per year. The annual recommended occupational dose is 50 millisieverts per year. An uncontrolled area, okay, an uncontrolled area now is that is occupied by anybody else other than personnel and patients. The dose limit is 2 millirems per week. 2 millirems per week. The annual recommended dose to the general public is 100 millirems per year. It's also going to depend on the amount of workload in that particular room. Now, what they've done here is they've implemented what is known as the use factor. The use factor, or the percentage of time during which the X-ray beam is on and directed toward a particular protective barrier, goes as such. the wall is going to be assigned a use factor of 1/4. Okay, because compared to everything else, it's only going to be used, the wall unit is going to be used 1/4 of the time versus the table unit, which is going to be used 3/4 of the time. The floor is going to be assigned a use factor of 1, and the secondary barriers will also be assigned the use factor of 1. That's an interesting number. The wall has a use factor of 1/4. Got it? You guys got it? Okay, you guys missed that question. I'll smack you. Most procedures are done using KVP at an average of 75. Okay, most procedures are done using a KVP at the average of 75, although they are designed to operate at up to 150 kV. Okay, so the average KVP that we use for most procedures is 75. It's also a good number. 75 is a great number. All right, radiation detection and measurement. Do we need to keep track of the amount of radiation that we're exposed to? All right, let's talk about this. First one here is a gas-filled detector. They can be ionization chambers, they can be proportional counters, or they could be Geiger-Müller detectors. So the way they work is as radiation passes through the gas-contained cylinders of any of these three, as radiation passes through the gas-contained cylinders, remember one of the properties and characteristics of X-rays is that it has the ability to ionize air. This is where these come in, okay? So as X-rays pass through the gas-contained cylinder, it ionizes it. The electrons released in ionization are detected as an electrical signal equivalent to the intensity of the radiation. Okay? So in actuality, it's not physically detecting radiation, it's detecting its ionization on air molecules. Okay, everybody got that? Mm-hmm. Second one here is the scintillation detector. Scintillation detector, generally used in nuclear medicine and CT imaging systems like your PET scanners. You guys know what PET scan stands for? Positron emission tomography. Okay. Now, certain materials emit a flash in response to the absorption of X-rays. We have scintillation detectors that detects the amount of this light flash, and it is proportional to the amount of energy absorbed by that particular material. Stronger the flash, the more radiation. Makes sense, right? Scintillation detectors. Photographic emulsion, your film badge. Your film badge. Okay, this is a monitoring device. It is radiation-sensitive film that is placed in a lightweight plastic holder. Now, within this plastic holder, you have different filters to filter out any weird readings. Okay? The remaining radiation ionizes the silver halide crystals within the film's emulsion. The film then is processed, and the amount of density on that film is proportional to the amount of radiation it received. This is review, guys. We've covered this before, right? Mm-hmm. Okay? So that's your film badge. So the greater the density, the more radiation that it received. By the way, where should you guys be wearing these monitoring devices?
On the collar.
On the collar. Why at the collar?
Eyes and thyroid.
Thyroid and eyes. Your eyes and thyroid are sensitive to radiation, so we're going to measure the amount of radiation hitting that area And it's going to be treated, it's a partial exposure, but we're going to treat it as what?
Whole body?
A whole body dose. You guys got tested on that, right?
Yeah, that's the answer I missed.
Okay, thermoluminescent dosimeter, or TLD. Within the hermetically sealed plastic holder, you will find lithium fluoride crystals. When these crystals become ionized by radiation, they go into this excited state. Okay, so they're storing this X-ray energy until they are ready to be read at a later time. So we're going to send the badges, every 3 or 4 months, okay, to the issuer. The crystals are going to be heated in a special measuring device that puts them back to their normal level. As they return back to their normal state, light is emitted that is proportional to the amount of radiation it received. Okay, got it? Let's go on to the next. OSL, or the optically stimulated luminescence dosimeter. I think that's what you guys have, right? The OSLs. Yeah? Okay. Now, within the hermetically sealed casing is aluminum oxide. Same thing. The tiny crystals trap and store energy from exposure to ionizing X-rays. And then the amount of exposure can be determined by scanning a green laser beam on the crystals and measuring the intensity of blue light that the crystals emit. So scanned by green light, the crystals emit a blue light, and the intensity of that blue light is proportional to the amount of radiation it received.